Welcome to Lecture 7, PhD in Artificial Intelligence. Artificial intelligence use of deep learning and statistics. It's a great combination. This is your Professor T. Freed Muhammad. This week, we embark on an exploration of the dynamic intersection between deep learning and statistics, with a particular focus on neural networks and deep generative models. We have been discussing on neural networks in quite depth. However, this is the extension or a transition of the use of neural networks in deep generative models. These advanced techniques are revolutionizing the field of statistics by offering powerful tools for modeling complex data structures that traditional statistical methods often struggle to handle. Neural networks, as discussed earlier as well, with their ability to learn intricate patterns through layers of interconnected nodes, are particularly adept at capturing non-linear relationships within the data. This capability is invaluable in modern statistical analysis, where datasets are often high dimensional and exhibit complex interactions. We have looked at healthcare, we have looked at the inventory control, we have looked and discussed in depth the route optimization, the robotics, and how these technologies rely on the artificial intelligence, which is based on neural networks, statistics, and many other methodologies in tow together. By leveraging neural networks, statisticians and data scientists can uncover hidden patterns and make more accurate predictions, thereby enhancing the overall analytical process. So the introduction to this topic will have an overview of the synergy between deep learning and statistics, and details with examples. How deep learning enhances traditional statistical modeling in high dimensional data. Now let's look into this in a robotics example to understand this topic in a little bit more depth. The synergy between deep learning and statistics has become a cornerstone of modern robotics, enabling machines to perform complex tasks with unprecedented accuracy and adaptability. Deep learning, particularly through neural networks, excels at processing vast amounts of sensory data collected by robots such as images, LiDAR scans, and force feedback. These models can identify intricate patterns and relationships within the data, permitting robots to recognize objects, navigate dynamic environments, and even predict the outcomes of their actions. Statistics complements this by providing robust frameworks for uncertainty quantification, hypothesis testing, and probabilistic reasoning. For instance, Bayesian methods help robots make informed decisions under certainty, such as estimating the probability of an object's location or the likelihood of a successful grasp in a cluttered workspace. In robotics, this combination is transforming industries like manufacturing, healthcare, and logistics. For example, autonomous robotic arms in assembly lines use deep learning to visually inspect and assemble components with high precision, while statistical process control ensures consistency and detects anomalies in real time. In healthcare, surgical robots leverage deep learning to analyze preoperative scans and assist surgeons during procedures, while statistical models assess risk factors and optimize surgical plans. The integration of these fields not only enhances the capabilities of robotic systems but also ensures their reliability and safety, making them indispensable tools in both research and practical applications. So we'll be looking into that how high dimensional data comes into the play in this lecture in more depth. The neural networks, I will not give more precedence to this topic at this moment because we had been discussing neural networks in quite depth earlier. The computational models inspired by biological neural networks composed of interconnected layers of nodes, also known as neurons. Image recognition, such as classifying handwritten digits in MNIST dataset, is an example that you can find by simple Googling and figure out how these guys have done the work. Google Scholar would be the best bet for you to find that information. So neural networks as universal function approximators for modeling complex non-linear relationships. Predicting housing prices using non-linear feature interaction is an area that we can explore in a little bit more depth to understand this concept. In the realm of real estate, predicting house prices is a classical example of a problem dominated by non-linear relationships, where traditional linear models often fall short. House prices are influenced by a multitude of interconnected factors such as location, square footage, number of bedrooms, proximity to amenities, and even intangible aspects like neighborhood reputation or market trends. These factors rarely interact in a straightforward additive manner. For instance, the impact of an additional bedroom on the price of a house may vary significantly depending on the size of the property, its location, on the current demand in the market. A small increase in square footage might have a marginal effect in a suburban area but could dramatically boost the price in a densely populated urban center. Traditional statistical models, which assume linear relationships, struggle to capture these nuances, often leading to oversimplified or inaccurate predictions. Deep learning models, particularly neural networks, excel at uncovering these non-linear relationships by automatically learning complex patterns from large datasets. For example, a neural network can identify that the relationship between house size and price is not constant but instead follows a curve, where price per square foot might decrease as the size of the house increases, reflecting diminishing returns. Additionally, neural networks can model interactions between features such as how the combination of a prime location and a modern kitchen renovation might disproportionately increase a home's value compared to either feature alone. By leveraging these capabilities, real estate professionals and data scientists can build more accurate and adaptive pricing models, ultimately leading to better decision making for buyers, sellers, and investors. The key components. Let's look into this with another example rather than the real estate one. Imagine you're trying to predict the price of a house. I think we should stick with real estate for a while. Using a neural network, a type of computer program inspired by how human brains work. The neural network has a few important parts that help it learn and make predictions. First, there is the input layer, which is like the front door of the network. This is where all the information about the house goes in. Things like the size of the house, how many bedrooms it has, how close it is to downtown, and the quality of nearby schools. Each piece of information is connected to the next part of the network, called the hidden layers. These layers are where the network does most of its thinking. Each hidden layer has lots of tiny units called neurons, and each neuron takes the information from the previous layer, multiplies it by a number called weight, and adds another number called a bias. The weights and biases help the network figure out how important each piece of information is. For example, the network might learn of being close to a good school adds a lot of value to the house, while an extra bathroom might not make as a big difference. After the weights and biases are applied, the neurons use something called activation function, like reinforcement learning or ReLU, to decide whether to pass the information along. The ReLoop helps the network understand complicated patterns, like how the price of a house might go up to a lot if it is a small and downtown, but not as much if it is a big and is in the suburbs. So finally, there are the output layers, which is like the exit door of the network. This is where the network gives the final answer, the predicted price of the house. The output layer usually has just one neuron, which takes all the processed information from the hidden layer and turns it into a single number. The whole process from input to output lets the neural network learn from lots of examples and figures out best way to predict house prices, even when the relationships between features are not simple or straightforward. So sentiment analysis in natural language processing is also an area that you can conduct research by going on Google Scholar or IEEE Explorer or your school library. And that'll allow you to read how people have applied these key components into sentiment analysis using natural language processing, natural language understanding, and later natural language generation with the generative pre-trained transformers. Training neural networks, optimization via backpropagation and gradient descent. I would strongly suggest you to conduct research on this to expand and enhance your knowledge. Gradient descent is a statistical term that helps us a lot to learn in terms of pattern recognition, training a neural network to detect fraud in financial transactions. Since I had a chance to work with Bank of America, I know firsthand when the merger happened with Merrill Lynch in Bank of America, we were given the task to figure out how to find out the mortgage fraud in terms of Bank of America's liability to take care in advance before taking over the entire organization. So I had a first-hand look at the data sets of mortgages. So overfitting and regularization, techniques like dropout, L1, L2 regularization, and early stopping to prevent overfitting, improving model generalization in medical diagnosis. Let's look into this in a little bit more depth. To improve model generalization in medical diagnosis, one of the most important steps is to ensure your dataset is diverse, representative, and high quality. Since medical data often varies across populations, hospitals, and geographic regions, a model trained on data from single source may struggle to perform well in real-world setting. For example, if a diagnostic model for skin cancer is trained primarily on images of fair-skinned patients, it must or it might not generalize well to the patients with darker skin tones. To address this, you should include data from multiple demographics, medical facilities, and imaging devices. Data augmentation such as rotating, flipping, or adjusting the contrast of medical images can also help the model become more robust by exposing it to variations it might encounter in practice. Additionally, cross-validation techniques like k-fold validation ensure the model performs consistently across different subsets of the data, reducing the risk of overfitting to a specific data set. Another key strategy is to use regularization techniques and advanced model architectures that inherently promote generalization. For instance, dropout layers in neural networks randomly deactivate some neurons during training, preventing the model from relying too heavily on specific features. Transfer learning is also highly effective by starting with pre-trained models, one trained on a large dataset like ImageNet, and fine-tuning it for medical diagnosis. You leverage general features the model has already learned, reducing the need for massive labeled datasets. Finally, ensemble methods or ensemble methods, also known as, which combine predictions from multiple models, can improve liability by averaging out individual model biases. For example, in diagnosing disease like pneumonia from X-rays, and an ensemble of models trained on different datasets might perform a single model, leading to more accurate generalizable results. The contrasting deep learning's data-driven approach with traditional statistical inference, and comparing its logistic regression and deep learning for customer churn prediction. I would strongly suggest you to conduct research on these topics using the Google Scholar, because people have done extensive work on contrasting and comparing of the techniques. Deep generative models that learn the underlying distribution of data to generate new samples. Generating realistic images of human faces, or GANs, is an area that I would strongly suggest you to conduct research, and let me share with you a little bit of my findings. Deep generative models, especially generative adversarial networks and variational autoencoders, have revolutionized the ability to create a realistic human face or human faces that are almost indistinguishable from real photographs. These models work by learning the underlying patterns and distributions of facial features from large datasets of real human faces. For example, a GAN consists of two neural networks, such as a generator and a discriminator, that compete against each other. The generator creates synthetic faces, while discriminator tries to distinguish between real and fake images. Over time, the generator improves its ability to produce high detailed and convincing faces, capturing nuances like skin texture, lighting, and even subtle expressions. This technology has applications in entertainment, gaming, and virtual reality, where lifelike avatars or digital characters are needed. However, it also raises ethical concerns, such as potential for misuse in creating deep fake content. One of the most impressive examples of deep generative models in action is Style GAN. A variant of GANs are developed by NVIDIA, which can generate hyper-realistic human faces with remarkable consistency. Style GAN achieves this by controlling different aspects of the generated images, such as facial structure, hairstyles, and skin tone at various levels of detail. This allows for fine-grained adjustments, enabling the creation of diverse and unique faces that don't actually exist. Beyond GANs, and variational autoencoders also play a role by encoding faces into compressed latent space and then encoding them to generate new variations. These models are not only useful for creative industries but also for data augmentation in training other AI systems, such as facial recognition models. However, as the technology advances, it becomes increasingly important to implement safeguards to prevent misuse, such as generating fake identities or for fraudulent purposes. Variation autoencoders I just discussed in quite depth. Probabilistic models that encode data into latent spaces, as I mentioned. Anomaly detection and manufacturing by reconstructing normal data is also at our fingertips when we start using VAEs. Generative adversarial networks, as I discussed earlier, I will not go into much detail. Two network systems, generator and discriminator, competing to produce realistic data, as I just mentioned earlier. Creating synthetic data for training medical imaging models is also in the books for us. GANs in statistics. Using GANs for data augmentation and imputation, as just mentioned earlier, augmenting limited data sets in rare disease research, such as vaccine creation and all that jazz that comes to our domain of research. The Bayesian deep learning, it's also probabilistic in nature, combining deep learning with Bayesian inference for uncertainty quantification. How uncertain it is that tomorrow it will be raining or not, or snowing. Predicting stock market trends with confidence intervals is also an area of research that you can look into while learning this artificial intelligence course, embodying statistics and deep learning, or reinforcement learning, as per se. Reinforcement learning and statistics, they're using neural networks to model decision making process in dynamic environments. We are optimizing supply chain logistics with reinforcement learning. We have discussed that in extensive details in our previous discussion, so I would suggest you to revisit these concepts. Neural networks for time series analysis, recurrent neural networks or RNNs, and long short-term memory LSTM that we are using these days in the generative pre-trained transformers using the ChatGPT, Claude, Mistral, Gemini, or XYZ, Zephyr are some of the examples. For the sequential data, forecasting energy demand using historical consumption data can also be looked by time series applying the neural networks. Explainability in deep learning, techniques like SHAP, S-H-A-P, and LIME, L-I-M-E, to interpret neural network decisions. Explaining loan approval decisions in fintech is another area that you can look into while you're searching or enhancing your knowledge looking at the house prices prediction. Ethical consideration in deep learning, these are addressing bias, fairness, and privacy in deep learning models. Auditing facial recognition systems for demographic bias is also a significant area for us to look into. Healthcare analytics, applying deep generative models into electronic health records or EHRs. Since I just have discussed how this is helpful, I would suggest you to conduct research on how people have applied health analytics using artificial intelligence. In Google Scholar would be your best bet. Generating synthetic patient data for clinical trials, so that can also be done while making sure that the biases are removed. The biases can never be removed in totality, but are limited. The financial model is another example, using neural networks for risk assessment and portfolio optimization. Predicting credit default risk with deep learning is an area that you can conduct study while looking at the house pricing as well. So let's continue in the next lecture. See you soon.